Continuing from the previous video, I have two more Belousov-Zhabotinsky reaction variants to test out. This first one was planned to be part of the chemistry demonstration show I used to perform. I made a whole lot of solution, but it turns out that the reaction takes too much time to work it into an hour-long show. So these giant bottles have been eating up all sorts of space in storage. This is the classic version and uses Cerium 4 as a catalyst. Altogether, we need 4 solutions. With the one marked C, add the concentrated sulfuric acid slowly to about 500 milliliters of water. This generates a lot of heat. When I made this solution, I used an ice bath to help control the temperature. I'm using the same ferroin from the previous video now that I'm convinced the 2013 expiration date was just a suggestion. Okay, here's the lineup. I already have the potassium bromate solution in the reaction beaker atop the stirrer. The first addition is the malonic acid potassium bromide solution. I'm running this reaction at a 100 milliliter scale, so each of the first 3 solutions are equal volumes, 100 milliliters, and there's 6 milliliters of ferroin. As we saw in the first video, it should generate a little bit of bromine and turn an amber color. Clearly, that's not happening. I'm going to keep going anyway and see what happens when the cerium solution and ferroin get into the mix. So next up, 100 milliliters of the cerium ammonium nitrate solution in dilute sulfuric acid. Obviously the solution is colored, but at this stage there is not supposed to be a color change, which is good because there wasn't one. The 6 milliliters of ferroin are up now. Remember, ferroin is colored blue in an oxidizing environment and red in a reducing environment. With the sulfuric acid and the cerium 4 present, this is an oxidizing environment, and the change to blue is exactly what we'd hope for here. Given that this is an oscillating reaction, we're hoping for obvious and repeating color changes. As the cerium 4 is reduced, it becomes colorless, so we're left with only the blue color of the ferroin. When the oxidation part of the reaction slows down and it starts turning into a reducing environment, the ferroin should go to red and indicate that change. The process continues, and when all is said and done, we should have 4 distinct colors that oscillate in a regular pattern: green, blue, violet, red, and then back to green. Well, we have something like an oscillation here. It started with the green, and then went to blue, and it was a lovely blue indeed, but then it went straight back to green. The oscillations seem to go between green and blue, and as the reaction progresses, it seems like a little reddish-purple tinge develops. This tells me that something is wrong. In the previous video, we saw that the malonic acid solution might degrade a little in storage. I've prepared a 50 milliliter test batch of fresh malonic acid potassium bromide solution, and we'll see how that goes. Once again, I'm starting with the potassium bromate solution already in the reaction beaker. Adding the malonic acid potassium bromide still fails to produce an amber color. Well, let's add the cerium ammonium nitrate. Oh, by the way, only the malonic acid solution is new. Everything else is the same. So now we'll add the ferroin. I just love colored vortices. So we have the green to start. And if we just wait for the moment where it actually starts the reaction, we do get a transition to blue. So we're on the right track. And it transitioned to green. So we still have some sort of failure and the fact that the first two solutions didn't produce an amber bromine color again indicates that perhaps the potassium bromate is no good either. But there is something else interesting that happens. This is a couple of minutes into the reaction, and as you can see, a whole bunch of bubbles appeared. As we learned in the last video, this is an indication that the old malonic acid solution is in fact no good. I can confidently get that off my shelves, but I'd have to mix up more of that solution and some of the potassium bromate to see if I can get rid of the potassium bromate too. The problem is there's another variant I want to try, and my supply of malonic acid is running very low. So let's move on, and if I have enough malonic acid left over, I might try this one more time. The good news about this next one is that all of the chemicals I'm adding to the reaction are solids. Honestly, this is just for fun because I'm on a BZ kick at the moment. This reaction was in my notes with the others, and I never had the chance to try it out, so we'll see it for the first time together. With the exception of the sulfuric acid, here's the lineup. And I don't have to wonder if the solutions went bad. Imagine that. We'll start by adding 25 milliliters of sulfuric acid to 250 milliliters of water. The sulfuric acid I'm using was extra from another reaction I did a while back, and it's starting to eat the cap on its temporary storage bottle. I hope dissolved cap won't inhibit this reaction at all. I'll leave it to cool for a little bit before proceeding. Okay, let's measure the temperature. Good enough. The next step is to add 3 grams of malonic acid. And once it's in there, it'll take a minute to dissolve, and once it looks clear, we can continue. Looking good. Next up, the potassium bromate. Oh no, that was the manganese sulfate. The reagents are all good, but this time the chemist is stale. Oh well, let's throw in the potassium bromate now. Alright, so it turned orange. Now what? I'm leaving this in real time because the first color change takes about 20 seconds, and then the oscillation interval speeds up a bit after that. Okay, now we're talking. This reaction will go on for another 30 minutes or so, with the oscillations getting less and less frequent over time. Towards the end, we will start to see some more carbon dioxide bubbles forming. As I said in the last video, these types of reactions have been thoroughly studied, and the overall BZ reaction is described as 2 main processes, both of which produce elemental bromine. Process A is a 3-step process that generates bromine through 2 ionic electron transfer steps. Process B is at least 5 steps involving radicals and another electron transfer. These 2 processes are in constant struggle with each other. Regardless of how the bromine is formed, it reacts slowly with the malonic acid to form bromomalonic acid, but it can only react with the enol form rather than the diacid. Process B is where the catalyst comes into play. In the first reaction, cerium was the catalyst, and in this one, manganese. There's even some autocatalysis going on in there. Volume 2 of Shakashiri's iconic chemical demonstrations devotes a whole chapter to oscillating reactions and goes into great detail on the BZ reaction mechanisms. It's a fascinating read, but you may have already guessed that some higher level chemistry knowledge is a prerequisite to even follow along with the explanation. It is fascinating though. Before we wrap this up, remember that both of these reactions use a dilute, but still rather strong solution of sulfuric acid. Before we dump them down the drain, we need to neutralize the acid. I use this 5-liter beaker, but any good-sized bucket will work. I fill it up to about 3 liters with tap water and add a generous helping of the key ingredient, sodium bicarbonate. It will settle, so stir it up. A little more. Give the stir bar a quick dunk. And notice the addition of gloves. It's important to wear heavy gloves whenever you're working with concentrated acids or even dilute solutions of the strong acids. Sure, as long as you wash off any spills or drips quickly, you'll be fine. But why take the chance when gloves are cheap and easy to get? Anyway, pour the acid solution into the sodium bicarbonate solution slowly to avoid it going over the top. That's also why I don't fill the 5-liter beaker past 3 liters. This does produce a fine mist of everything in this cocktail, including the acid, so don't breathe anywhere near this reaction or your lungs are going to hurt. And you can't just rinse those off. Once the bubbling stops, flush this whole mess down the drain and rinse out your beaker for the next neutralization. I did each run's waste in fresh bicarbonate solutions just to make sure they've been neutralized properly. In the next video, I'll try out a couple of chemiluminescent reactions with luminol. I have 3 reactions and, as usual, have no idea what to expect. I guess we'll see how it goes. Thanks a lot for watching, and I'll see you next time.